Last time I showed you how velocity selectors work and a little bit about mass spectrometers and cyclotrons. We're just going to practice applying the ideas you guys are working on to a mass spectrometer because it's really not difficult. But basically, mass spectrometers, basically what they do is they use the velocity selectors you guys have been looking at, and they also use the electric fields and the magnetic fields in order to actually find masses of charges. So we're sort of lay things out here a little bit, and maybe we'll make it too crazy, but it's probably the easiest way to look at it, and we'll connect this to something else later on. I'm going to make two sections here, something like this. Okay, good. And I'm going to make a little. There we go. Okay, something like that. All right, so I'm just going to break this part into two main sections for what we got going on here. Okay, so first of all, at the bottom part here, this is going to be our velocity selector down here. So this is our velocity selector, just this bottom part down here. So I've got an electric field and a magnetic field going through that thing right there. And I'm going to make my electric field going towards the left. Okay, this one's a little crooked here. We're going to make the electric field going towards to the left. Okay, and I'm going to draw my magnetic field. I'm going to make dots for my magnetic field. So I got a magnetic field here as well. And you already know it's a velocity selector. So when we have our charge in here, here's my little charge. Maybe it's a proton. Okay. I know it's a velocity selector, so I know my proton is going to go nice and straight through the hole. That's what I want, it's nice and straight. Okay, so it's a velocity selector. So at the bottom there, I've got two forces. I've got my electric force and I've got my magnetic force, because both those fields are there, and I know those two forces are equal to each other. That's why it's a velocity selector. Now, in the second part, when the charge goes up here, there is just going to be a magnetic field. That's it. So all we have up here is magnetic field. We're not going to have an electric field. So since we have a magnetic field, it's not going to go straight. It's going to go in the shape of a circle. So when the particle goes through there, okay, if you use your right-hand rule number 1, your gun's pointing straight up. Your fingers are pointing out of the screen for the magnetic field, and your thumb is towards the right. So I know that my force is in that direction. There's my magnetic force will be in that direction. I can also tell that by looking at the bottom here, because my electric field is to the left, which means my electric force is to the left because it is a positive charge. Well, if my electric force is to the left, my magnetic force has to be to the right, so they cancel out. And I'm keeping the exact same magnetic field on the top and the bottom to make things nice and simple. So when this thing goes to the top, all we have is the magnetic force. And of course, this is what you guys took before. That magnetic force then creates centripetal force. So I've got three forces. I've got Fe is equal to Fb down here. Fb is equal to Fc up here. And since we're just going to use the same magnetic field, all the forces are equal to each other by association. They're all good. Okay, so as this particle goes in here, it's going to then create a circular path. Okay, something like that. And then what they can do is they can measure the radius of that path to figure out the mass of the particle and stuff like that. Okay, so this is the basic idea behind a mass spectrometer and how a mass spectrometer works. And of course, you know the speed coming out. And if it's a heavier particle or a lighter particle, it'll do something different. So if it was a lighter particle, it would have a tighter circle because it's lighter. It's easier to curl around. There's greater acceleration for the same force. So the lighter ones, this would be the lighter ones would be, and the heavier ones are out here. And they look at the distributions to sort of see how what the differences in the distributions are to get the average atomic mass that you see in the periodic table. Okay, so let's sort of look at this a little bit and practice this a little bit. So let's say we have our particle coming in, and let's say it's going at 3.2, oops, wrong, all right, let's get rid of that. I want 3.2 times 10 to the 4 meters per second is how fast it's going. And let's get rid of the two pathways here. Let's just worry about the one charge. Let's get rid of that. Okay, and let's say over here when it goes across here, it hits, let's say it hits 12 millimeters away. So it hits 12 millimeters away from the opening. Okay, so let's find out a couple things. Let's find out the electric field and the magnetic field. So what would the electric field be and what would the magnetic field be? Okay, now before we do that, let's give you a little visualization that might help with this a little bit to sort of see what's sort of going on. Okay, so here's a little simulation showing exactly what we're working on. They don't have the velocity selector sort of shown down here, but that's okay. So the particle is going to come in and it goes nice and straight. Now, of course, for us, we've got a velocity selector here. That is this part right here, going nice and straight. And then when it hits the magnetic field, that is when it curls around. Okay, so there's a nice little circular path, perfect circle. There's the radius labeled and everything, and it goes nicely around. Okay, so that particle hit right about there. And I can show you if I take this particle and I make it heavier, and we do the same thing, you can see that a heavier particle has a much bigger radius. Same charge, same V, because it went through velocity selector, but since it's heavier, it's going to make a much bigger circle, and this is what they look at in terms of atomic masses and stuff like that. Same thing if I make it a really light particle, okay, same type of thing, but a much tighter circle, so it just sort of whips around super quick. So this is the idea behind using mass spectrometers and using circular motion of particles in order to figure out how heavy they actually are. Okay, so it's actually kind of cool. All right, so this is literally the exact same setup that we're working with. We have the speed of the particle coming in. We're going to find out the magnetic field and the electric field in the setups. Okay. Okay, so back to our question. We've got the setup here. We got the force involved. We're going to try and find E and B. Okay, well, I've got three forces. I've got my electric force, which is QE, and that's equal to QVB at the beginning. And then in the second part, my QVB is equal to MV squared over R. And what I can do is all these forces for what we're doing, our little situation, they're all equal. So I can tie them together any way I want. It doesn't make any difference. I can make these two equal. I can make these two equal. I can make these two equal. I can solve for whatever I want. Okay. So for example, I could solve for the electric field by tying these two together. So that means that the electric field would be equal to mv squared divided by qr. Even though those two forces don't exist at the same location, I've got my magnetic field the same everywhere, so I can actually tie them together. Well, I've got my m, it's a proton, I've got my v squared, I've got my q, I've got my r, I can calculate what my electric field would be. And if I do that, I get an electric field of around, I'll use my red, of like 1780 newtons per coulomb. So that is my electric field strength. Okay, now what about my magnetic field? Well, for my magnetic field, okay, well, in a magnetic field, I could tie equations together any way I want. I can also go back to the basic velocity selector expression. Remember, we had the expression velocity selector E divided by B. Well, I have V and I have E, so I can just use that one right there, which is actually a combination of those two, to solve for my magnetic field. So my magnetic field would be E divided by the velocity. So I can take that 1780 and divide that by the 3.2 to the power of 4, and I've got a magnetic field of 0.056 Teslas. The magnetic field will always be way smaller than the electric field. Okay, so really that's how these work, and really there's nothing really new to it. It's basic F equals QE, basic F equals QB, and basic S equals MV squared over R. Tying them together, no big deal. Okay, just make sure you use the radius here, not the 12. You don't want to use the 6 millimeters when you do the radius calculation here. But other than that, that's pretty much it. So it's relatively straightforward, just basic forces and tying things together. Okay, it's actually, I find this a lot easier than doing some of the electric field stuff that you guys have done. Okay, so let's try another one and let's practice that as well. Okay, so for this one, we got a uranium-238 nucleus shooting 4,700 meters per second, hits 32 centimeters away. we are going to, again, let's find the fields, including drawing them. And I'm going to start by actually drawing them. Okay, now, first things first, there's a couple things you can do here. It doesn't make any difference, a couple ways you can do it, but we'll just figure it out. We got the positive charge coming up down here, and the magnetic field shoves it to the left. Well, if the magnetic field is shoving it up to the left over here, that means my electric force has to shove it to the right. So if my electric field and force have to shove it to the right, you know, this has to be the negative plate, this has to be the positive plate, okay? Or you can look at it this way, the electric field has to go this way. Okay, so I know my electric field has to go to the right, so the electric force is to the right, because my magnetic force is to the left. Okay, then you can also then use your right-hand rule type thing to figure out what the magnetic field would look like. Again, you can take your subatomic gun, it would point straight up. The magnetic force is to the left right here. The magnetic force is to the left, going this way. That's why it goes to the left. So your thumb would point left, your fingers pointing up, and then the 3 remaining fingers are pointing into the screen. So these have to be X's, and we keep our magnetic fields the same, so something like this. Okay, so there's my diagram. Okay, all right, so now, of course, to do this, I will need the mass and charge of this. We've done this before. You need the mass, the charge, uranium-238. And for the mass, should around 3.97 times 10 to the negative 25 kilograms. And the charge would be, with the 92 protons, but 1.47 times 10 to the negative 17 coulombs. Okay. So I got my basic properties, and now I can find my E and B. Last time I found E first, let's find the B first this time. So for my B, I know that mv squared over r is going to be equal to qvb at the top. We've done this type of thing before. My v's actually cancel out. Okay, they can cancel out something like this. So then my magnetic field, just take the Q over there, would be mv divided by qr, and of course the radius would be the 16 centimeters, and make it 0.16 meters, not the 32. So if we do that, hopefully we get around 7.9 times 10 to the negative 4 teslas, or 0.79 milliteslas, and that would be my magnetic field. Okay, for my electric field, again, you could tie forces together or just use the velocity selector expression. It doesn't make any difference, but the electric field would be the velocity times the magnetic field. Well, I've got my V, it's right there, 4,700. I've got my B. So if we multiply the two together, we should get electric field hopefully around 3.7 newtons per coulomb, and that's going towards the right, and my magnetic field was X's. Okay, so again, that's basic mass spectrometer type questions. Again, I actually think they're pretty, kids usually find them pretty easy. You know, they're very, very complicated machines. Like actually trying to build one, operate one, I mean, the really, really complicated. But the actual basic physics behind the idea is actually pretty straightforward. Okay, nice things, just tie the forces together and find what you can, no big deal. And then being able to use your right-hand rule and your electric field ideas to figure out how to draw the actual fields on the diagrams based on what the particle is actually going to do. Of course, if this had been a negative particle, all the fields have been reversed because it would have gone the opposite way in order to get the same situation. Okay, so that's how the mass spectrometer type stuff works.